Okay, so this is going to be slightly different. It's more a generic modeling paradigm, talking about piecewise linear functions a little bit, and we've already introduced them and seen them a little bit, so this is sort of a refresher. And then the next two lectures are going to be more, again, about application modeling. So I'll talk about piecewise linear approach for univariate functions, so functions that depend on one variable, and then also about this approach for multivariate non-convex mixed integer nonlinear optimization problems. And we'll see a sort of a first hint as how one might solve mixed integer nonlinear, non-convex mixed integer nonlinear optimization problems potentially. Okay, so if we have univariate functions GI, so they map a single variable that is real to the real numbers. We can also generate this to separable functions by just doing approximations of building up approximations using these univariate functions. And our approximations are going to be piecewise linear approximations. In this figure here, we have some nonlinear function, that's the solid blue line, and there's a piecewise linear approximation that has 4 breakpoints and then the endpoints of the interval. So very important here is that we need to assume somehow that our variables are in a bounded set. So x is between a lower and an upper bound. Otherwise, there's too many breakpoints. But in many problems, you can assume this, and you can often find these bounds in a pre-solved step potentially. So what I'm going to show you is how to get piecewise linear approximations and solve and then replace the nonlinear function by this piecewise approximation and solve a mixed integer linear optimization problem. And we could potentially refine this later on. So notice that the approximation is not exact. For example, up there at the top, you're sort of chopping off quite a lot of that function. And if you wanted to look for the maximum of that function, then you might not get the correct answer. But you could potentially refine these approximations. So I'm given a univariate function that maps a finite interval. L and U are finite bounds. And we're going to find a piecewise linear G hat that approximates G in this interval. And I'm not going to talk about the quality of the approximation. So that depends really on the spacing of the breakpoints that I'm going to introduce. So I'm going to start off by creating these breakpoints and segments which go from 0 up to D. So very similar to what we did earlier this morning. I have my interval that goes from a lower bound to an upper bound, and I'm going to introduce D breakpoints, and I'm just going to assume that these are equidistant, but there's really no reason to do this. You can move them around to better approximate the function. And then at these breakpoints, I need to evaluate my function. So I have a nonlinear function that sits here, and I need to evaluate my nonlinear function at these breakpoints. So and that's a finite number of these evaluations. And so those are going to be called yk, and the breakpoints are going to be called bk for breakpoints. And that's my nonlinear function g of x here. So that's the picture you should have in mind. And then it's really, this is probably about, I think 11th grade calculus or 10th grade calculus, I think, where you see this, that you can build this linear approximation. So x are the variables. If x is in the kth breakpoint interval, then you build this approximation. And you can just quickly check that that's correct. If you plug in bk here, then this term cancels with the denominator, and what you end up is, if you plug in bk, you end up with yk minus 1 plus yk minus 1, correct? And if you plug in bk minus 1, this becomes 0, that cancels, and you get yk minus 1. So you have a linear function, it matches the two endpoints. Very easy. You can also just compute the slope and the intercept by forming these values, and then I can represent this affine approximation as ak plus mkx. So there's somewhere here, there's this linear approximation that's ak plus mkx for in this interval here. And so now I'm going to put all these together and show you how we can model these problems as a mixed integer linear optimization problem. So the first approach is a multiple choice approach. So we introduce binary variables that tell us whether we are in an interval or not. So zk is 1 if we're inside this interval. So if I'm inside this interval here, if this is my current point, then I want zk to be equal to 1. And if I'm not in that interval, then I set it to 0. And so there's a way of doing this, of rewriting this by using additional variables wk that lie in this interval. And then I'm going to, so the wk's are variables that lie in this interval that's sort of lower bounded by zk and upper bounded by zk. So what happens here is if zk is 0, then the wk will be 0. If zk is 1, then wk lies between these two intervals. And because this is a special ordered set of type 1, our old friend, that means there's only one wk which will be non-zero. All the other ones are going to be 0. So x is going to be the sum of these wk's. And then the piecewise linear approximation is just taking all the pieces, plugging in the wk, so that's the x value, and multiplying the offset by zk. So now if zk is 0, then this part is 0. We set the wk is 0 because zk is 0. They vanish. And only for one intercept, only for one linear approximation where zk is equal to 1, will I get mkx plus ak. So this is the formulation there. Okay, and so this was developed by Jaroslav and Leyffer, and it sort of works well for breakpoints that are not too many breakpoints. This is quite a good approach. There's an alternative formulation, actually two alternative formulations, and this is a convex combination model. So again, I have binary variables zk, which are 1 if and only if I'm in the interval bk minus 1 to bk. And now I introduce a binary variable lambda k, and I'm going to write my x as a linear combination of these breakpoints. So I take all my breakpoints that I have, and I multiply them by lambda k. And the lambda k are non-negative, so that makes this a linear combination, and they sum up to 1, so it's a convex combination. So lambda k is summing up to 1, and non-negative means this is a convex combination of the breakpoints. So my x is a convex combination of the breakpoints, and there's multiple ways of writing this, right? I can, if I have this point here and the half, I can write it as a half times this plus a half times this, or I can take in other breakpoints. So there's multiple ways of writing this, but we're going to eliminate most of those. These next two constraints say that if you're now looking through all the intervals from the left to the right, and you're setting the lambda j's to 0 if you're not in the current interval. So remember, zk or zj here indicates which interval you're in. So if the zk is 0, you're setting all the lambdas up to that point to 0, which means they don't participate in the convex combination. Sorry, the other way around. This is the one where you set the previous ones to 0. This is the ones you set the next ones to 0. So there's 2 of these constraints. And then the special ordered set constraints. So what these constraints do is they ensure that if I'm in this interval, then all these lambda k's will be 0. That's this constraint here. And all the lambda k's that are here will be 0. That's this first constraint here. And so when I write it as a convex combination, only these 2 guys are participating in my convex combinations, which is what I want. And then if I do that, then this constraint tells me now that I get the y that I get out, the function value that I get out is a convex combination of the function values, my intercept values. So that's actually the right condition here. So because it's a linear function, you get the correct linear function value there at that point. And I'm going way too slow here. There's a way of modeling this without these additional variables, without the zk's. And that's what is called a special ordered set of type 2. So special ordered set of type 1 is one where exactly one variable, or at most one variable, is non-zero. A special ordered set 2 is one where at most 2 adjacent variables are non-zero. So that's what I want here. I want this special ordered set of type 2 that says at most 2 adjacent ones are non-zero, everybody else is 0. And if you declare, and you can do this in the solvers, that's implemented, I think, in most mixed integer linear optimization solvers, including, and there's support for it in AMPL, for example, then we can write these constraints that we had earlier without the complication of having the zk variables. So we can eliminate all the zk variables here, and we're just left with the constraints that tell us that we have a convex combination, and the convex combination of the x point then corresponds to the convex combination of the y point with the same lambda variables. So this is really a neat concept, special ordered set of type 2. Does anybody know what a special ordered set of type 3 is? Oh, is it? I don't know. You should think about that a little bit, because we're going to do that next. So we're going to play games with these special ordered sets. You can go as high as you want to. Sorry? Yes, it's actually for 2 dimensions, but yeah. So in what I'm going to do now is, and I'll just draw this here, and then you can ignore the slides. So just pay attention to this. So now I have 2 variables, x and y, and I have a function g of x and y that I'm going to note as z that comes out of the board. And I'm going to discretize my domain. So this is a very coarse discretization, and I'm going to introduce triangles. And because I'm not doing finite element analysis, I don't have to worry whether the triangles are the right way around or not. And now I'm going to replace my function by piecewise linear functions and linear functions on these triangles. And so you know that a chair with 4 legs rocks, but a chair with 3 legs never rocks. And the reason is because there's a unique hyperplane that's defined by these 3 points here, a unique linear hyperplane. So by having these 3 values, I have a unique hyperplane, and now I play the same game. I'm going to have my special ordered set of type 3 that you suggested by saying, if I'm at this point here, then at most the 3 adjacent ones are going to be non-zero, and I form convex combinations. That's it. It's easy. And you can do this in 4, in 8, in 24 dimensions. So that's all. So here's just a picture that shows this in a different way. That's a triangulation of x1 times x2. So now we're interested in forming multivariate approximations. We choose breakpoints. So the BK are now two-dimensional. They're no longer, because you have two variables. And we partition this interval between Li and Ui. So there's a lower bound here, and an upper bound, and another lower bound, and another upper bound. And we're going to approximate g of x in the same way. This is exactly the same formula that I had previously for the special ordered set of type 2. So nothing has changed, except these guys are now vectors. So this is now a vector, and x is a vector because we're in R2 or in R3. But it's the same principle. And it satisfies the SOS d plus 1 condition, if and only if. So for a d approximation of a d-dimensional function, I have a d plus 1 condition, if at most d plus 1 adjacent are non-zero on a single simplex. So that's my condition. So I can now form this linear approximation. I have a linear approximation in this interval. I find out where I am. I write this point as a convex combination of the three adjacent ones, and then I can work out what my intercept is. And that's all given here. And again, this is a linear expression now. So this is a linear function. So that's of course a linear term. This is a linear function, and that's a linear function. Generalizes to as many dimensions as you want to. There's one pitfall, and that is that if you drive n, or the number of dimensions, too large, you're going to need p to the n special ordered set variables. So p is the number of discretization points in each dimension that you take. And here I've only had 3, but this is a very, very coarse approximation. So you really want something that's much, much finer and to get a good approximation of your function. So in the next lecture, we're going to look at expressions for power systems engineering. And they have nonlinear functions that have 8 variables. And so if you discretize those, even over a small range, you probably want something like 10 breakpoints maybe. So you will have 10 to the 8 variables. That's okay. You can solve problems of 10 to the 8 variables, but it's maybe not the most efficient way of doing it. Luckily, there's a really cool way of decomposing nonlinear functions. And we've already looked at this. We've looked at the computational graph. So here's sort of the idea that if you have a nonlinear function h of x, or h of x and y, we can often decompose it into, by just copying the variables that we have, and then just writing it as a concatenation of univariate or bivariate functions. So it's either a univariate or a bivariate function. The notation here means that at the jth level, I either have 1 or 2 variables that I've mixed together in some nonlinear way. So it could be multiplying the 2 things, could be exponentiation, then it's just a univariate, and then the last one is just that. So, and we saw an example yesterday, and this is the very same example. So here there is a function at the top there that's again motivated by the power grid examples, cosines and squares. Those are expressions that turn up in the power grid. And you can write this function by taking the independent variables, putting them into the bottom into this directed acyclic graph. It's not unique, and you can formulate the function in that way. And now, the cool thing is if you look at this table on the left here that shows you all the functions, you no longer have a function in 4 variables. Instead, you have 4 functions in at most 2 variables that you need to do approximations for. And that can be potentially much more efficient when you're doing these special ordered set approximations. So one way of doing it would be to leverage this decomposition to get an approximation. Any questions about this? Yes?
When you describe special order set of model 2, then how do you say which variables are adjacent? Like For an SOS2, you can simply put them in a list and say that.
Right. So you're right. So for a SOS2, I do the SOS2. I do it real quick up here. This is SOS2. It's easy to see who is adjacent. This picture here is SOS3. And I don't say adjacent. What I'm saying is they have to lie in the same simplex. And now if I go to SOS4, I'm not sure I can draw that, then I'm going to have little pyramids somehow. This is not the right picture. I don't know if I can draw a pyramid. But you have little pyramids that you put together. And in higher dimensions, you need to invite somebody else to draw a picture. I can't do that, unfortunately. But so you can still do these decompositions, but they become much harder. So that's a good point, actually. So in 2 dimensions, this meshing process is probably quite efficient. This becomes harder in 4 dimensions, I think, as well. Or 3 dimensions, SOS4. But you have the same condition. So you're inside some, now it's a volume, you're inside a volume, and you decide which volume you sit inside, and that tells you which to do. Cool, but we don't want to do that. We want to do this approach, which keeps us where I can draw pictures to illustrate what's going on. Okay, this is just an example. If you did this for the active power expression, you have 8 independent variables there. And if you did this decomposition, you need 5p squared plus 3p SOS variables versus p to the 8 variables. So that's typically much, much smaller, even if n is not very large. Yeah, for p equals 1, this is smaller than this. But I think already for p equals 2, this is smaller than the other one. I haven't checked that. Okay, and so this generalizes, and it's called factorable programming, and we'll talk more about this later in the course. So we assume that we have functions that can be written as combinations of products of unary and bivariate or binary functions. And so we assume that we can always rewrite our optimization problem. We don't have to do it. You don't have to do it. This is the modeling language, and the solver agree to do this behind the scenes. And these functions, we can always write our problem in this way. And then this is basically a very general approach for non-convex mixed integer nonlinear programming. So Baron, Quen, they're all based on this technique that you internally reformulate the problem into simpler functions, component functions that are univariate or bivariate, and you work on finding convexifications or good approximations of those univariate or bivariate functions in a way that is linear, for example, that allows you to solve mixed integer linear problems. So a very general decomposition approach. And I'm way over time, so I'm not going to show this. There's some references there. But no, we don't need to look at this either. So we can do these piecewise linear approximations. They're very easy to do in the one-dimensional case. They're tractable in the two-dimensional case. And if we want to do higher dimensional cases, we reformulate our problem. Or internally, the solvers reformulate the problem to get problems that only evolve univariate or bivariate functions, like in this computational graph here. And so this is called factorable programming or factorable optimization, and we're exploiting this fact in finding good underestimators. Cool. Any questions about this? Yes? Explain SOS2 again. Okay. So I can go through it again. Where am I? It's not that. It's that one here. So I have, let's see if I can do this on this picture here. So I have a nonlinear function, a new nonlinear function, and I start off, so this is my nonlinear function g of x, and this is the x-axis here. I start off by discretizing between my lower bound and my upper bound. So I'm assuming that x is a bounded variable. I must assume that. And then I evaluate my function at these breakpoints. So the b case are, this would be b0, this is b4, and then corresponding to the breakpoints, I evaluate my function. So this is y0, y1, up to y4. Okay, and now I introduce these lambda variables, and the lambda variables are, they also correspond to the breakpoints. So there's a lambda 0 up to lambda 4, and the sum of these lambda variables is equal to 1, and they're greater or equal to 0. So that means that this is a convex combination. We talked about the convex hull, and the convex hull is if of a set that was constructed by having sort of variables lambda which were non-negative and summed up to 1, and doing all combinations between all feasible points. So this is very similar to what we had earlier. And the SOS2 condition is that if I find some point, I use this point here, if this is my x, then I only want the lambdas which are corresponding to this interval to be non-zero. So I want lambda 3 and lambda 4 to be non-zero, but lambda 2 and lambda 1 have to be equal to 0. So only the two adjacent lambdas, so they're next to one another, are non-zero. And now I work out where I am, and let's assume for the sake of argument that this is sort of a half, that each of them contributes a half. Then this intercept here, the way this works out, the value of that intercept, the value of y that you compute there, this is y, is given by, again, this convex combination of the y case that I have. So just with these two lambda values. And the reason for saying you want only two adjacent ones to be non-zero is if I had more of them, then the x would be correct, but the y would now be a convex combination of more points, so it would actually not be correct. And instead, it would be a different point. So the fact that I'm in this interval I have a linear approximation, and the lambdas tell me exactly, they map the x to the y in this linear approximation. And that generalizes exactly to this case. So now you have to imagine you have a linear function here again, and you're mapping to this linear function. I don't know if that was too much. I'm sorry if it was too much. Okay. You had a question.
So, like, while solving through solver, so because which adjacent lambda value will be non-zero.
Yeah.
How solver detect this? These two adjacents are non-zero.
Excellent question. So the solver will actually come up and say all of the lambdas are non-zero. That's the relaxation. So the solver is stupid. The solver just says all of them are non-zero. So now you need to tell the solver, I don't think that's what you mean. I think you mean that these two are 0, or these two are 0, and that's called branching. So, and we haven't talked about this yet. So, so you can branch on these special ordered sets. So you will compute a relaxation, and most likely all of them are non-zero. And now the solver has to figure out, given that the x that they agree on lies here, that gives you an indication of which ones you should set to 0 and which ones you shouldn't set to 0. But you need to do this in a branch and bound process. So you typically, that means that we would, and this is going into tomorrow actually. You typically, we call this problem a root node, and so we solve a relaxation. So we solve the problem without the SOS2 condition. And then we get a solution that violates this condition, and now we need to pick lambdas that we set to 0. So we say lambda 1 is equal to 0, is lambda 2 is equal to 0, or lambda 3 is lambda 4 is equal to 0. And we create two new problems. And in this example here, the two new problems satisfy the SOS condition now because it's so simple. But in general, there would be more of these variables that you would need to set to 0. So it's not as simple. But notice that the solution has to lie either in this problem or in this problem for this simple example, right? That's sort of the, is that the only ones? No, there could be more. So, okay. I'm not correct. So, but you can do branching on these special ordered sets. And that's one way of dealing with this. And we'll talk about this tomorrow. So the solvers don't find the lambdas, the correct lambdas.
One more question.
Yeah.
Is it really the case why we are taking the adjacent lambda non-zero? Because we are taking the piecewise linear approximation, that linear function, which
Yeah.
do that those discrete points. Is it the main reason, or because if I approximate this function, the continuous function, with the other linear function that is not adjacent lambda value?
Right.
So it will be not the best approximation than this.
Right. Yes. Yeah. That's a good point. So if you took different ones, if you took a linear combination of y0 and y4, then that's your approximation. And so that's not a very good approximation, right? If you took a linear combination that involved all three of these, then it would be probably something that looked like this. And so we want to narrow it down. We want to go into the sets, the special ordered sets. That's a very good point. Thank you. Yes?
Which one is better, SOS1 versus 2?
Oh, which one of these two formulations is better? I think this one is better, but I'm not sure. Ashutosh might know better. So there's two ways of writing this, right? One is I can write this with additional binary variables, or I can branch and solve it directly in this way. I think this is better because it has fewer variables. And there's been some papers written on comparison of these things. Yeah?
How to decide number of breakpoints?
Excellent question. I have a slide for that. So I should pay you money afterwards. So, okay, so really you want to do a good approximation, and at the same time you want to not have too many breakpoints. And so deciding where the breakpoints are, that's probably a modeling question. So you can probably graph out these functions, and you can graph out where the breakpoints are. And this is probably not a good selection of breakpoints there because you have big gaps at the top. So you might want to fill in an extra breakpoint there. But the answer is you would map this out and maybe have some idea of what the approximation error is. You can work out the approximation error on each of these intervals, for example. You might want to have a uniform approximation error. So the error in this first interval is quite small, it's quite large in the second interval. And so maybe one way of doing it is to say, I want a uniform approximation error.